Following up on our discussion of oscillations, we are going to be taking a look at wave motion. Now, I'm not talking about the back and forth wave motion that you might see at the beach. I'm talking more about a continuous, smooth, oscillating situation. The ripples on a pond like you might see, where you just see wave after wave after wave all present in this one shot. This is more like the example of the waves that I want you to think about in this discussion. You can imagine the surface of water, and you have a duck there or something, and if you watch that duck, you see it move up and down like it's oscillating. It's floating, but because the surface of the water is rising and falling, the duck or whatever is also rising and falling. And a wave is like a continuous sequence of oscillations that run through the length of a material. Some of the waves that we might encounter that obey the sorts of properties we're discussing here, the strings on a stringed instrument, so like a guitar, we get oscillating waves when you pluck a string. You can make an argument that a flag with the multiple ripples in it has wave-like behavior. We also see wave-like behavior with sound. Now, I said the word see. If you take a look at this image on the right of a nuclear explosion, it might be very hard to see, but if you look closely above the cloud, you'll see these slightly paler lines that are paralleling each other and have slight curves to them. Those are shock waves. Those are actually compressions in air as a result of the explosion. And those shock waves are, as the name suggests, an example of a kind of wave. These are the kinds of waves that we're going to be discussing. It's like an oscillation that is allowed to travel from one location to another. The thing that a wave does is it transfers energy, but without transferring material. In the case of the tin cans tied together with string, you cause wave-like oscillations in one can. Those oscillations travel down the length of the string to the other can, but it's not like there is an actual transfer of material. It is simply energy that is getting transmitted from one tin can to the other tin can. A common quantity associated with waves is intensity. And to understand intensity, you can think about it as the loudness of a sound or as the brightness of a source of light. And let's stick with the latter, and hopefully you'd be able to make sense out of comparisons with sound. But imagine a source of light. If a light is very bright, it has higher intensity. But what does that mean? It means that it's putting out more energy each second. So a dim light might put out 10 joules of energy per second, and a bright light would put out 200 joules of energy each second. Since we're talking about energy per second, we're really talking about power. And power is measured in watts. Think of a light bulb and the wattage on a light bulb. You can imagine a 40-watt light bulb, a 60-watt light bulb, and a 100-watt light bulb. And just from your own experience, you know that as the wattage increases, the brightness of the light would consequently increase as well. So more intensity means more power at the source. But there's also another thing going on. We can focus the brightness into a small area. Imagine a magnifying glass and sunlight, and you can focus that sunlight onto a very small area. And that very small area, there is a huge intensity, but even just adjacent to it, the intensity is very non-existent. So the area that is covered by the light also factors into it, a very small area, means that there's very high intensity where there is illumination. So what do we have? We have that intensity increases with the power and decreases with the area that is being illuminated. The more area that is illuminated, the less intense the source. Whoops. This is a bit like a famous story told about the ancient Greek mathematician and scientist Archimedes, the same Archimedes of the law of buoyancy. And the story goes he was hired by some royal guy, whatever, to try and sink a ship without having the benefit of a navy or even a catapult. So Archimedes thought, well, imagine focusing the rays of the sun onto a small area, and if you get that area exactly in that focus, you can get a pretty high temperature, and that might be enough to ignite the wooden boats. Well, this video right here is of someone who uses mirrors to illuminate a small section of a car, as you can kind of see in this picture right here. But let's play the video, because the person running this experiment also has a nice little device for measuring the temperature of the car's surface. So let's take a look. And let's proceed through the warning. And here is the meter that he's using to measure the temperature. Probably a reasonably warm summer day, so that the temperature is in the 130s for the surface of the car. I mean, we've all felt the surface of a car on a hot summer day, and it can be pretty warm. Now, these mirrors are being used to focus the rays of the sun onto this very particular location on the car. You can see this one area on the car that is very brightly illuminated by the sun. And he's going to examine the temperature at that location. 64 seconds into exposure, and it's already over 100 degrees higher and rapidly rising. And it was rising so rapidly that he rushed over to basically stop the experiment because he didn't want to damage the car. So this was an example of focusing light into a very small area, resulting in a very high intensity. If you don't focus the light, if you have a source that emits light equally in all directions, if it's equally in all directions, we call that isotropic, and this would be isotropic radiation. The sun, to a very good approximation, emits light equally in all directions. And so the sun would be an example of an isotropic source of light. Any object that is the same distance from an isotropic source is going to see the same brightness. The source will appear to have the same intensity. On the other hand, if you move in closer, the source will appear brighter, and if you move further away, the source will appear dimmer. For an isotropic source, we have a formula that allows us to calculate how intense it appears. Intensity depends upon both power, the power of the source, and the area being illuminated. So we take the power of the source, capital P, and we divide by the area being illuminated, and that's actually a sphere. I know you're only seeing a circle on the screen, but if you imagine this in 3 dimensions, it's actually like the inside surface of a sphere centered on the light source. And we want the surface area of a sphere, because that's the area being illuminated. The formula for the surface of a sphere is 4 pi r squared. So P over 4 pi r squared gives us the intensity for anybody some distance r away from an isotropic source radiating power at a rate of capital P. There's some classic ideas. One of them is called a Dyson sphere. These are fanciful, hypothetical constructs, huge constructs, mega, giga, tera, peta, exa structures, just inconceivably gigantic because they surround a star. They're called Dyson spheres after a British physicist by the name of Freeman Dyson. And on the left, we see an artist's conception of a Dyson sphere in the final stages of construction. You can see the star at the center, and you can see the final pieces of the sphere being put in place so that it entirely surrounds the star. And the image on the right is an artist's conception of what it might look like if you were actually inside the Dyson sphere. And so you could see sky on the far side of the sphere. Intensity has units of watts per square meter. Intensity, in many cases, decreases with the square of the distance from the source. That's not true for lasers, though. But for many sources, even an ordinary light source, if you double your distance from the source, then the intensity goes down because you're moving further away, but it goes down by a factor of 4. If you're doubling the distance, R goes up by a factor of 2, R squared goes up by a factor of 4, the intensity goes down by a factor of 4. Think about this question. We have a light source that is presumably not a laser, and we have a light detector that is measure 16 watts per square meter at a particular distance. We are going to double the distance between the source and the detector, and we're also going to double the power of the source. If we do both of those things, what is going to be the intensity measured by the detector? 2 watts per square meter, 4 watts per square meter, 8 watts per square meter, 16 watts per square meter, or 32 watts per square meter? Think about it. Feel free to ask me questions at the start of class. Let's do a numerical example. The sun, of course, emits light, and to put this into context, if you are standing at noon when the sun is directly overhead and it's a cloudless day, the intensity that you see, and you're not supposed to do this, by the way, the intensity that you see is 1,373 watts per square meter. So prolonged exposure to that intensity will blind you. If you look at the sun for too long, it blinds you. So that should give you some sort of idea as to what an intense source is. In this question, we're being asked how much energy does the sun emit each second, and in order to answer this question, we are going to assume that the sun is a perfectly isotropic source, and that's a pretty good approximation. But we also need to know how far away Earth is from the sun. And that, if this were a test question, I would give that to you. It's 1.50 times 10 to the 11 meters on average. That's going to be our value of R. And we want to solve for capital P. We have our expression for the isotropic point source, and capital P, the power, is equal to 4 pi R squared times the intensity I. We just said R is 1.50 times 10 to the 11. Don't forget to square it. Times 4 pi times 1,373. And the sun's power output is 3.88 times 10 to the 26 watts. So in 1 second, the sun puts out 3.88 times 10 to the 26 joules. And I really can't put that into good context. You know, it's the energy output of the Earth for X number of years. It's a lot of energy. So there's our total energy in 1 second. That's all I want to say about intensity at this point in time. What I want to do is I want to discuss general wave behavior. And waves tend to come in two broad categories. One of those categories is transverse, the other is longitudinal. A transverse wave is much like what you see on the screen. You can imagine a string, and we jerk it up and down, and we send a pulse traveling down the length of the string, and the pulse shows what we had is that the string itself is moving perpendicularly to the direction in which the pulse is traveling. The pulse travels down the length of the string oscillates perpendicularly to its own length. And this is a transverse wave. Longitudinal waves, the oscillations are actually parallel to the direction of propagation. It's like a compression wave that you see in this image. But what I'm going to do is I'm going to show you a couple of videos that I think better display transverse and longitudinal waves. Here's an example of a transverse wave using a slinky. And we don't need the music. And, okay, so here we go, sending transverse waves. You can see that the hand that is causing the motion is moving parallel to the tabletop, back and forth. That's also perpendicular to the length of the slinky itself. And you see this pulse traveling down the length of the slinky. So it looks very sinusoidal. That's a transverse wave. A longitudinal wave is a compression wave. And we see the same experimenter. Let's take a look at a longitudinal wave. And there it goes. You can see that the hand is moving back and forth down the length of the slinky, and you can see a compression wave. And the compression wave travels down the length. This is a longitudinal wave. It's like a shock wave. So that's what we mean by transverse and longitudinal waves. Hopefully that helps you visualize these things. Whether they're transverse or longitudinal waves, they are waves. I'm showing you again the image of the atomic explosion and the very faint ripples in the air. Those are shock waves. Those are longitudinal waves. Sound waves are longitudinal waves. There is wave-like behavior if we think about the alternating compression and rarefaction of a wave. Remember the slinky video, and you could clearly see where the coils of the slinky were compressed together, but on either side of the compression were rarefactions, where the slinkies were further separated from each other than they would be if the slinky was at rest. So in a compression wave, we have alternating compressions with rarefactions. A sound wave can be visualized as an oscillation in pressure. If there's no sound in the air, the pressure would be whatever atmospheric pressure is. But as a sound wave travels through the air, as a compression wave, we get this compression where the pressure goes up a little bit, and adjacent to a compression is a rarefaction, where the pressure is decreased a little bit. Now, what we have on the screen is a plot of delta P, the change in the pressure. If the change in the pressure is positive, there's compression. If the change in the pressure is negative, there's rarefaction. And so we see alternating regions of compressions and rarefactions. And so we see the wave-like behavior manifest in this format here. A wave doesn't have to just be one type or the other type. A wave can experience both transverse and longitudinal waves at the same time. A classic example is an earthquake. The seismic waves that travel at the surface or immediately underneath the surface can create both transverse waves that would cause back and forth motion, but also longitudinal waves that would cause to and fro motion. And when both pass through the same region at the same time, what you can kind of get is a sort of a circular or elliptical motion. Not only moving around in a circle, but you would also get up and down oscillations as well. So an earthquake, you got a lot of different waves passing through, some trying to move you left and right, some trying to move you north and south, some trying to move you up and down, all at the same time. Now, let's try and quantify some things about a wave. And one of the most important things in a wave is the speed at which it travels, its propagation speed. So when you saw a pulse travel down the length of the slinky, that pulse had a propagation speed. Whether it was a transverse pulse or a longitudinal pulse, it traveled at a finite rate through the slinky. Excuse me, that's the propagation speed that we're talking about. What can we do to understand propagation speed? We're going to start by looking at an oscillating string. Now, you can take a thin string, you can take a thick string, and you can start them oscillating. And let's assume that you're using the same amount of energy for the thin string as for the thick string. For the thick string, there's just more mass. And if the amount of energy you're supplying is finite, well, 1/2 mv squared. If there's more m, there's going to be less v. So heavy strings, you're going to have a slower propagation speed than light strings. But another thing that influences this is how tense the string is. Basically, the more tense the string is, the greater the force of one piece of string on another piece of string. And there's basically less energy needed by the pulse to stretch the string further. If the pulse is traveling through an already tense string, it travels more easily because it doesn't have to pull the string as hard. There's already a lot of hard pulling in the string. The pulse doesn't need to do so much in order to be able to travel down the length. So really, when we factor these two in together, we might be tempted to say that the speed depends upon the tension and the mass and the length. And wouldn't it be nice if we could say V is equal to the tension times the length divided by the mass? But if you do a unit analysis of tension times length divided by the mass, you get units of meters squared per second squared, not meters per second. A genius idea. If we look at it from the point of view of the units, the square root of meters squared per second squared is meters per second. So perhaps the speed of propagation along the string was equal to the square root of the tension times the length divided by the mass. That's actually correct. This is a very sloppy derivation, but it turns out that this is the correct formula to determine the propagation of a wave on a stretched string, where the tension in the string is Ft, the length of the string is capital L, and the mass of the string is m. This, however, is not the formula I would recommend be on your formula sheet for the next exam and for the final exam. Rather, we tend to characterize strings by a property, the mass per unit length. How many kilograms per meter is this string? You might use only 30 centimeters, but you're going to be given the property of kilograms per meter. This is sometimes called the linear mass density. It's often represented by a lowercase letter mu, Greek letter mu. It's equal to mass divided by length. And if we use this string property, then our expression for the speed of propagation in a string is the square root of tension over linear mass density, square root of Ft over mu. Think about that formula and look at this question here. Suppose we have a copper string. Maybe it's like a guitar string, piano string, whatever. It's a string made of copper. And for whatever perverse reason, we want to have another copper string that has half the speed of propagation as the original. Which of the following would accomplish this? Can we increase the tension in the string by a factor of 4, decrease the tension in the string by a factor of 4? Can we use copper wire with twice the diameter of the original wire, or can we use copper wire with half the diameter of the original wire? This is an absolutely terrible test question. It's an absolutely terrible test question because there are 2 correct answers. Think about it. Let me know if you have questions at the start of class. Let's do a numerical example. We have a horizontal string, it's fixed at one end, and the other end is essentially attached to a freely hanging 12.3 kilogram mass. The string has a linear mass density of 37.2 grams per meter. Be careful about those units. And so the question is, what is the speed of a wave traveling down the length of the string? The linear mass density has standard units of kilograms per meter. So the linear mass density is 0.0372 kilograms per meter. The tension in the string is provided by the hanging mass. If that hanging mass is in equilibrium, the gravitational force acting on it down is balanced by the tension force in the string pulling up on it. So the tension is going to be equal to 12.3 times 9.8. It's equal to 120.54 newtons. The speed, tension divided by mu, then take the square root, is 56.9 meters per second. Is that fast? Well, it's over 100 miles per hour, but that's actually not terribly bad. It's not a terribly unusual situation for a stretched string, especially a metal string. Any wave has a few parameters, and I don't care what kind of wave it is. There are general parameters that I want to discuss. One of those parameters is wavelength. Wavelength is represented by the lowercase Greek letter lambda. It has units of meters. And it is basically the distance from one part of the oscillation, one part of the wave, to the next identical part of the wave. So we often think of it as peak to peak. Lambda, the wavelength, the distance from one peak in a wave to the next adjacent peak in the wave. Units of meters. But another thing is frequency. Take a look at the 2 animations, and the dot that you see moving from left to right in the 2 different locations is supposed to represent the propagation of the wave. What we have are these 2 dots, both with the same frequency. They're oscillating up and down at the same rate. But the wave with the longer wavelength, the dot has to travel faster. So what we can see is that if I wanted to calculate propagation speed, It seems to go up as the wavelength goes up. So there's a relationship between propagation speed and wavelength. Is there a relationship between propagation speed and frequency? And the answer is yes. Now in this pair of animations, the wavelengths of the two objects are the same, but the frequencies are different. The upper one oscillates up and down very slowly. The lower one oscillates up and down very rapidly. And we also see that the lower one, which has the higher frequency, also has the higher propagation speed. So the propagation speed also seems to increase with frequency. If we combine those two observations, we might be tempted to say that the speed of propagation equals frequency times wavelength. And that's correct. There are no other factors needed. V equals S lambda. This V being propagation speed, the speed with which the wave-like effect travels through the medium. Take a look at this conceptual question. We have two strings, one is thick and the other is thin, and we connect them end to end to form one long string. We send a wave down the length of that combined string. So it's going to start at the thin, and then it's going to pass from the thin to the thick, or maybe we started at the thick, and then it's going to reach that junction going from the thick to the thin. Visualize this. Use your imagination. Which of the following do you think is going to change as the wave transitions from, say, the thick string to the thin string? Will the frequency of the oscillation change? Will the period change? Will the propagation speed change? Will the angular frequency change? Now, this is also a bad test question because there's more than one right answer. I'm sorry, I misspoke. I misread this. This actually would be an okay test question because there's actually only one right answer. So this would be a good test question. There's only one right answer. Sorry for misspeaking earlier. Be careful about your understanding of V in that formula. V equals S lambda. V is the speed at which the wave's effect travels through the medium. It is not the speed of the medium itself. The wave travels through the medium, and then the medium is left where it was before. The medium itself does not travel. We just have energy traveling through the medium. That V represents the speed at which the energy travels through it. While the energy is traveling through it, parts of the medium are moving, but it's not like all parts are moving at the same speed. The animation on the screen, we see this wave oscillating up and down, and some parts of the wave have a relatively high speed, other parts of the wave have hardly any speed at all. So that V can't apply to an actual piece of the medium. It applies to the energy, the effect that is traveling through the medium. That's enough. I hope that's enough. Bye-bye.